Alright, so obviously you guys knew I was going to be here, so this little video is to help you do these two worksheets here. Intermolecular forces worksheet 5, intermolecular worksheet forces number 6. So we basically went through all the bond types already: ionic, covalent, network covalent, metallic, and we're kind of going through each one very slowly. So I'm just going to give you kind of a quick run through of some examples of each one and just refresh your memory on the different types. We still have notes to get through, which we'll do tomorrow and Thursday, but I want you to be able to do these worksheets. I think you could do them right now, but I want to give you a little help so it's a little smoother process. When you're done with these worksheets, you're going to hand them in. So period 3, which is what you're in right now, you're going to hand these in at the end, and then you're going to be given this lab. I'll explain that again real quick at the end here. So this is not going to take very long, but we know there's ionic, we know there's covalent, there's polar and non-polar, we know there's network covalence, we know there's, did I say metallic? Metallic already. So those are the 4 types. Ionic, we already went through. Covalent, we just started taking notes on yesterday. Just remember there's 2 different types. So water, for example, is polar. PCl3, for example, is polar, but CH4 is nonpolar. All the Hanckel-Griffs, H2 would be nonpolar. Where it gets a little confusing on these worksheets, and I hope you know from the lab that the polar are slightly stronger than the nonpolar, right? So when we melted above the water, I think one of them melted, that was very nonpolar. So these are very weak as far as low melting points. They also don't dissolve in water. You know that. Nonpolar won't dissolve in water. But polar stuff will melt fairly easily, but a little bit harder to melt than nonpolar. So above the burner, for example, polars will melt above the burner. They most likely will, because they're still pretty weak compared to ionic and metallic and network covalent solids, but but they're stronger than the nonpolar. So anyways, where it gets kind of weird on the worksheets is if you have something like ethanol, so C2H5OH, we know that's covalent, all nonmetals. It's not a network covalent. I'll go through those in a second, but we know this is covalent. Now, is it polar or nonpolar? We have to learn more about forces of attraction, which is what this lab is going to kind of introduce a little bit, and we got to take some notes on that. But anyways, we don't know if this is polar or nonpolar. Well, I'll just tell you that alcohols are slightly polar, so that's why ethanol will dissolve in water. So if you come across something with an OH on the worksheet, it's going to be slightly polar. Now, the shorter the chain, the more polar it is. So if I have a whole bunch of carbons, okay, and we go out to OH here, so 1, 2, 3, 4, 5, so that would be pentanol versus ethanol. This is actually slightly less polar. It's actually more nonpolar because of this long carbon chain. But anyways, I'm just kind of giving you a little help for that, the worksheet there. So that's that. If you see something, I think acetone is on there. So acetone looks like this. So that's acetone. And you need a little help with that because it's confusing the way they draw it condensed and they put the CO at the end, which is stupid. So that's acetone, and it's actually pretty symmetrical. So acetone is very nonpolar, so keep that in mind, write that down. That'll help you on the worksheet. Another one they give you is benzene, which we've talked about, but they give you benzene as C6H6, which is right, but it looks like this. So this is a carbon, 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 double bonds alternating. So there's only 1, 2, 3, 4, 5, 6 hydrogens coming off here. So that's benzene, also very nonpolar. So it's very symmetrical no matter how you slice that thing. It's I didn't draw it very well. Each little part here, each bond, is exactly the same length as the other because of resonance with that double bond. Delocalized pi bonds, we already learned all that. Hopefully that makes sense, but I didn't draw it very well. So it's very symmetrical. That's nonpolar. I think that was it for the covalent stuff. So you know they share electrons just unequally polar, equally nonpolar. You don't really need to get into all the details, but that's for covalent. Network covalence, all you really need to know, SiO2, SiC, silicon by itself. That was number 9 in the lab, that stuff that's all along the railroad that Slade likes to take long walks by himself on. So anyways, silicon, network covalent. So group 14, carbon, silicon, germanium, tin. So carbon, diamond, right? Carbon solid, pure carbon, diamond, graphite. So I can write those down, diamond, graphite. So these, germanium, these are all the network covalents. I don't think you'll ever see anything else. In fact, those are really the only ones I know of as well. So those are your network covalents. Really, really, really high melting points. They don't have forces at all. They're all bonded together. We've talked about this already, but again, I wanted to list these are your network covalents. So I should write that, network covalent. Okay, so bonds hold all the atoms together. That's why they're so strong, except graphite. Graphite has these sheets, and then in between the sheets, we have these weak van der Waals forces, which is why graphite's kind of soft and why you can write with it. So those are actually pretty weak forces, but the sheet itself is network covalent. So that's just one exception, and because of that, actually, graphite can conduct because of those sheets, actually, and the way it's put together. Silicon can too. We talked about that. Same concept. That even though that they're very tightly bonded, very strong, they are able to conduct electricity. Some of them, because they have some similar properties to metallic bonding. So that's your network covalent. And metallic bonding. Metallic bonding, there's not a lot to say as far as real quick here for this worksheet, but some metals bond themselves, right? Copper has metallic bonding. Sodium has metallic bonding. Zinc. So individual metals have metallic bonding, really high melting points, just like ionic. Not quite as high as network covalent, but really high melting points. And the reason these are so strong, they have those electrostatic interactions. They have those positive cations surrounded by the sea of electrons. So the electrons are kind of moving around, but they're attracted to the positive ions. So Cu plus 2, Na plus, Zn plus 2. So that electrostatic Coulombic force is very strong. They're kind of like ionic. It's different though because ionics have positive ions, cations, negative anions, and that's a strong attractive force. Strong bond. This is strong too, but it's different because it's electrons with the cation. So that's metallic. Obviously metallic, they can bend, right? They are able to glide past each other, whereas ionic, when they slide, they repel. We talked about that the other day. So I'm just trying to hit everything here just to help you out. I think that's it as far as what you really need to know. I mean, in general, that's kind of what you need to know. But for these worksheets, there are some questions about dispersion and hydrogen bonding. We'll just see how you do on that. You could use your book, obviously, to help with that. So I guess that's it. So those are due at the end of the period. This lab you're going to get handed out here, period 4A. I'm going to give you a little time to work on your lab due tomorrow. Then you're going to get these, and I want you to start this today. So you're just going to do 1, 2, 3, 4. That's it. 1, 2, 3, 4. This data table, you're filling in molar mass, the width of the drop, number of drops to fill the well, and then height in the capillary tube. So the directions say put a drop on a plate. I don't have plates. I just have this plastic. I want to say this is like an old milk carton or something. I forget what this is, but you're going to drop the liquids, which I'll have in the back. Water, ethanol, propanol, butanol. I'll have those in the back labeled. So you're just going to put a drop. You're going to measure the width. All right. It also tells you to rank the liquids in order for each drop to completely evaporate. So you can fit, I'm hoping you can fit them all on here. I don't know how big some of the drops are. I actually haven't done this myself, but if not, I think I have enough pieces here where you could maybe use 2 per group. If not, you guys someone can cut this one in half. Let's see, 1, 2, 3, 4, 5, 6. Now we have 6 groups, so oh, that's one for, I can't count. 1 group for each one of these. I don't know, try and make it work just so you can see how fast they evaporate. You can figure it out. And This is your well plate, the little ones. I'm gonna have them in the back. Count how many drops of each liquid it takes to fill those up. And then I showed you, Kira, you are the capillary queen here. You're gonna be dispensing these to everybody. So when you're done with these, I'll have a beaker back there that you can put them in. Try not to break them, don't cut yourself. All right, but Kira's in charge of those. So those are your capillary tubes. You're gonna measure the height of the liquid in the capillary tubes. I guess the rulers are over here. If I forget to put them out, but they're over there. And that's it. So just do 1 through 4, and that's it. And you can put this away, and then we'll finish it up probably Thursday. But that's it, just 1 through 4. Because all this stuff down here with the probes and everything, I don't use this format. I don't use this technology, we'll call it. I use the other stuff we have, so that doesn't apply to us. All right, so I guess that's it. Hopefully that helps. And enjoy the rest of the day without me here, because I know you are enjoying it very much so, apparently. I'll see you tomorrow.